Computer Science and Engineering Colloquia features accessible talks by leading computer scientists and computer engineers from across the region and around the world.
Thank you very much for coming to today's Colloquium. I'm very pleased to introduce Tony Nowatzki. He's going to tell us about how architectural specialization can revive general purpose computing architecture research, which is really quite an exciting thing to be doing. In addition to the research, you can also ask him questions about composing piano concertos and windsurfing, and apparently at the same time. So with that, take it away, Tony.
All right, thanks so much for the introduction, and thanks for the invitation. Today I'm going to be talking about some of the work that I've done at the University of Wisconsin-Madison over the last few years. And hopefully by the end of this talk, I'll be able to convince you what future general-purpose architectures are going to look like. And I want to start off with just a few simple questions, like why is it possible to write unoptimized JavaScript code and render beautiful web pages on a cell phone? Or why is it possible that Netflix can analyze petabytes of data and give you a movie recommendation anytime you turn your TV on? Or why is it possible to have augmented gaming and augmented reality and 3D gaming on your mobile device and not have the battery run out in 5 minutes? Okay. All of these technological advances are due to exponential improvements in microprocessors over the last half century. And the amazing thing is, from the programmer and the user's perspective, all of these gains have come largely for free. So how does this work? Well, programmers write in high-level languages. This is compiled down to one of a few stable instruction set architectures. And these are run on something called on general-purpose microprocessors. Now, these have been getting higher and higher performance with each generation by using higher power structures internally in their microarchitectures. And they're supported on the bottom level by devices or transistors that have been getting more power efficient with each generation. So it's really the synergy between devices and microarchitectures that have led to all of these free improvements. But unfortunately, this is all coming to an end. Because of fundamental limitations in transistor scaling, devices are no longer consuming less power. What that means is that our general-purpose microarchitectures are limited in how they can scale. And at the top level, the future advances in consumer electronics and IT that we would have expected are now under threat. So I'm not the first to realize this. And the architecture community has reacted in largely one of two ways. The first way is to say, well, we don't need general-purpose processing. We can just build domain-specific accelerators for each problem that we come across, whether that's matching regular expressions or detecting pedestrians in a driverless car. We'll just build specific hardware for that domain. We can get very high performance at low power by focusing in our transistor resources on exactly the type of work that we want to do. We can also have a modular design by composing together these different units to target arbitrary workload sets. But unfortunately, if we rely on this, we give up on generality, and that's actually the cornerstone of providing transparent improvements to users. The other approach is just business as usual. Keep building general-purpose processors and hope for some sort of microarchitecture solution. Now, of course, this strategy will let us have generality and programmability, but since we're trying to target arbitrary workloads with very high-power microarchitectures, we're going to have a low potential for improvement going forward. So both of these approaches have significant problems, and to frame what I think is a solution to these problems, I'm just going to describe these quickly visually. So a domain-specific approach basically takes each application and treats its execution as unique and builds one domain-specific accelerator for each one. Whereas a general-purpose approach treats each application as essentially the same and builds one monolithic architecture to support all of them. However, what I'm arguing we can do is, if we look deeper at these applications, we'll find that there are phases of the program's execution that have striking similarities in terms of program behaviors. And these behaviors can be as broad as memory regularity, control criticality, data parallelism. And the key observation here is that these broad program behaviors actually exist across domains. And this observation leads to the big idea of my talk, which I'm calling behavior specialization. Now, there's two key hypotheses here. The first is that behaviors are exploitable by specialized architectures that can improve the performance or lower the power over a general-purpose architecture by many factors. And two, that we can find a small number of exploitable behaviors that can cover the majority of the applications that we care about. Now, if both of these are true, what will we have? Well, we'll basically have a general-purpose system that isn't tied into any particular domain. We'll be able to compose our architectures modularly out of simple components. And we'll be able to provide transparent improvements back to users. That's actually what we cared about from the very beginning. So the way this will work in practice is that programmers will write in high-level languages, and now it's a compiler's responsibility to identify how different program regions will be more or less suitable on different accelerators. And the binary will be run on something I'm calling a behavior-specialized core, which is composed of a general-purpose core and several behavior-specialized accelerators, or BSAs. Yes?
This will probably become clear soon, but can you give us some intuition on the length of these dynamic executions? Are we talking dozens of instructions or millions of instructions?
In this work, I'm talking about regions of the program that are in the range of thousands to tens of thousands, or sometimes even millions of instructions. So I'm trying to target a wide range. Yeah. And I have more, and ask this question again later, I'll give you some more detailed data. Okay, so the main contribution, and then of course, then dynamically during the program's execution, depending on what the compiler decides, we'll just transition between using one of these different accelerators. And the main contribution of my work is just the identification of this paradigm for improving general purpose processing, showing that it works on real workloads and provides significant benefits. Now, the way that I did this research was I started off with one behavior and one accelerator, and then generalized this to multiple behaviors. And then foundational to all of these were some early advancements in the compiler that I made earlier on. And I want to just take you through the steps of these research and highlight the main contributions in the next 4 slides. So the first thing I did was something called Dataflow specialization, and I'll get to what the program behavior is behind this in a moment. But what this allowed me to do is cover 30 to 60% of general purpose workloads in a very simple Dataflow-based accelerator that is actually relatively small compared to the general purpose core, and allowed me to get overall 30% speed up and even more energy efficiency. And the interesting thing here is that Dataflow architectures, even though they've been around for a long time, actually become especially effective inside a behavior specialization system. So the tools and the insight behind this research let me generalize this for multiple behaviors and multiple accelerators. And what I found is that by creating accelerators for a few intuitive behaviors, allowed me to cover even more, actually majority of the programs that we looked at. And here we were able to get integer factor improvements on speed up and energy efficiency. But of course, there are some workloads where we really need 10x, 100x, and 1,000x benefits on them. And the key is that these workloads have different kinds of properties. I'm going to call these structured workloads for this talk. And the key properties here are that they have very high concurrency, very well-behaved memory access patterns. And when I built a programmable behavior-specialized accelerator for these, I was able to get orders of magnitude improvement on this very important class of workloads, which approached the benefits of custom hardware. And the reason that this works is that we can use domain-agnostic mechanisms to specialize for the same behavior, program behaviors, that custom hardware is specializing for. And then finally, across all of these different accelerator approaches, we require very efficient code schedulers to map computation onto the exposed hardware resources. And the way that we would typically do this is for each architecture that we have, we take an existing compiler and add new heuristics or algorithms. And what I've actually discovered is that there are common and architecture-specific compiler responsibilities that can be abstracted through an integer linear formulation, allowing us to create a general mathematical formulation for the code scheduling problem. So this simplifies the amount of work that we need to do to explore new accelerators, and also can actually give us better solutions than a heuristic-based approach. So overall, that's a summary of my research, like some initial accelerator compilation work, which fed into the Dataflow specialization work, generalized it to multiple behaviors, and focused in on more structured workloads. In this talk, I'm going to focus on the behavior specialization aspect of the work, and for each of these, talk about the main challenges. So there's basically 4 main challenges. The first is figuring out what is the program behavior that we're going to specialize for, and why do we even think that we can create an architecture that's better. Second, how do we extract this program behavior from the program in a way that makes the architecture simple and can cover enough of the program to be useful? Third, how do we exploit this with efficient architectural mechanisms without exploding our power or area budget? And finally, how do we organize this to make a very efficient processor system that's actually better than current generation processors? In this talk, I'll focus in great detail on the Dataflow specialization part of the work, and I'll talk about the other 2 at a higher level at the end if there's time. So what is the behavior behind Dataflow specialization? Well, this is just something called control non-criticality. And I'm going to explain what this program behavior is with an abstract example, and I'll go over a more concrete example later in the talk. So imagine we have a series of instructions executing in some abstract processor, and then here I'm highlighting the control instructions in green. And this basically forms a series of dynamically executing basic blocks. So the critical path through the control here is 9 instructions, and the critical path through the computation is 12 instructions. So regardless of the architecture for this particular program, the control is not on the critical path. So, okay, fine, this is some program behavior, but why is it important? Well, this program behavior is prevalent across many types of workloads like graph traversals, linked list traversals, sparse matrix multiplication, dynamic programming, and even more importantly, we can actually exploit this program behavior with well-known data flow architectures. Now, in order to explain why a data flow architecture makes sense on this type of workload, I need to explain what the difference is between a general purpose architecture and a data flow architecture. And for the architecturally minded among you, when I'm saying general purpose, what I'm talking about is von Neumann machines. So a general purpose architecture logically performs instruction by instruction execution and maintains the precise state at every instruction. Now, what this allows it to do is speculate at arbitrary instructions in this instruction stream and easily recover at low cost. And so this gives general purpose architectures a great advantage in dealing with control critical workloads because it can speculate those critical control instructions without too much cost. The data flow architecture, on the other hand, does dependence graph execution and does not maintain the precise state at every instruction. So it's going to be much harder to recover at arbitrary control instructions. But on the other hand, since we're expressing the program dependencies explicitly in the program representation, we expose more instruction-level parallelism. We can actually execute this instruction-level parallelism with lower power hardware. So general-purpose architectures are better when the control is critical, and data flow architectures are better when the control is not critical. So how do we extract these control non-critical program regions from the program? And what I'm really asking here is, if we consider our program to be executing as a series of phases, where sometimes we prefer to be executing in the general purpose processor, and sometimes we prefer to be executing in the data flow processor, how do we extract those program regions that we would like to execute on the data flow processor? And this decision is going to have implications both on the complexity of the architecture and how general our approach is. So we have a number of options for what kinds of codes that we'd like to target. For instance, we could build a data flow architecture that could execute arbitrary code, or we could build a data flow architecture that could target just inner loops or looping traces. Now, if we target arbitrary code with the data flow processor, we can potentially execute any instruction on the data flow machine. But this is going to be have very high costs in terms of the design complexity. And that's because our data flow architecture would have to support arbitrary procedure calls, recursion, instruction non-locality. And these are just things that are difficult to support in a power and area-efficient way inside of a data flow processor. But on the other hand, if we target something simpler, like an inner loop or a trace, we can avoid this complexity. The unfortunate consequence of doing that is just that the total amount of programs that we can cover would be much less. What I'm suggesting that we do is take a compromise between these and target something called nested loops, which are just loops embedded inside of each other. And I'm really talking about inline nested loops here. And so here, again, the design complexity is going to be low because we don't have to support these complex features. And the coverage is potentially much higher. And intuitively, the length of the program regions that execute inside nested loops are actually much longer, too. That can help mitigate the overhead of transitioning. So even assuming that we want to use nested loops for the data flow architecture, we don't always want to be executing in data flow mode. And the question is, well, how often would I really want to be executing in a data flow processor in some idealized sense? So that's what I'll explore here. And I'll compare the execution of a high-performance general-purpose processor with that of some ideal data flow processor. And the ideal data flow processor that I'm talking about here does not do any control speculation, but it has as many execution resources as we want. So what I did is I compared the execution of these workloads across many irregular across many irregular workloads, and found that almost 2/3 of the time I'd rather be executing in data flow mode. But not only that, but in many of these program regions, we're getting 2 to 4x speed up. So overall, there's a high potential for actually using data flow specialization. And now the question is just, how do we exploit this with efficient architectural mechanisms? So the way that I'm going to explain this is I'll first explain the system at a high level, and then I'll go into more details of the Dataflow architecture. So the way that our system works is that we take a program and look at the different nested loops. And a compiler is going to use path profiling information to decide if the control is not critical, to decide whether or not the Dataflow architecture looks like a good workload, a good architecture. Then it will be compiled down to a binary and run on our core architecture, which consists of a general purpose core and a Dataflow processor, both integrated behind the cache hierarchy. Now, the reason that we integrated them at this level is because it allows us to quickly switch between the two architectures without migrating a lot of live state. And I'm calling our architecture NSDF for non-speculative Dataflow. So the way this works during the execution is, again, we're going to be executing as a series of phases, and I'll just zoom in on one phase to explain what's going on. So first, the general purpose processor, before we reach the Dataflow region, we'll begin streaming in the configuration. When we reach the Dataflow region, we'll power down the non-stateful components of the general purpose core and switch over execution to the Dataflow processor. It will execute for some time, and then once it's complete, we'll power back up the general purpose processor and resume execution there. So now, I just want to talk about what is the architecture behind this Dataflow processor. So I'm going to employ many fundamental, yes?
So who decides what inlining you do, and can your loop nests have sequential loops, or does it have to be, can you have sequential loops?
Let me answer your first question. The compiler is responsible for deciding which loops to inline. So it'll actually make a hierarchical decision of should I just target this inner loop? Should I target the more broad loop? And it's using some heuristics to decide whether or not the control will probably be critical or not. What's the second question was?
You show a loop inside a loop. Can I have a loop after a loop?
Yes, absolutely. Yeah. And the reason that you might want to do that is because you might not want to have the overhead of transitioning back and forth. So I'm going to employ, in this Dataflow architecture, I'll employ many fundamental Dataflow principles like the Dataflow firing rule to tolerate changing memory latencies. I'll employ explicit control dependencies that I won't do speculation on. And I'll use distributed processing elements to get high amounts of instruction level parallelism. There's two main optimizations that allow us to get very low power execution. And the first is because it relates to the Dataflow firing hardware. And we can actually, and the way that this works is that every instruction in our nested loop will get explicit operand storage. And so firing this instruction just is a matter of checking whether or not the operands are present. And the reason that this can work so simply is because we're targeting a static region of the program where we know all the instructions that could execute. And the reason that I bring this up is actually because if you look at what a general purpose microarchitecture is doing, we're basically either simplifying or eliminating many of the very high power structures there. So we'll get much lower power execution. The second optimization has to do with the distributed processing elements. And specifically, the overhead that we care about here is the additional latency and contention on the interconnection network anytime any of the functional units try to communicate with each other. So the way that we mitigate this overhead is by grouping together individual functional units into groups. I'm calling these compound functional units. Now, values that flow inside the compound function units don't need to flow on the interconnection network, so they experience less latency between these operations, as well as reduced contention on the interconnection network. So with these two main things in mind, I can explain the NSDF architecture. Again, the NSDF is integrated behind the L1 cache next to the general purpose core. I'm showing NSDF is large here, but it's actually quite a bit smaller than the general purpose core. NSDF is organized around a set of compound function units, of which it supports about each one supports 2 to 5 instructions. We've chosen to use 8 compound function units here so that it's possible to get a higher instruction level parallelism than the typical general purpose processors in a good program region. These are supported by an instruction management unit, which house the instruction definitions as well as any live operand storage. And the IMU will be able to issue 1 instruction per cycle. These communicate over a multi-bus network for transmitting any live values. And some of these compound function units will have access to the memory interface, so that we actually won't need to use the core to supply the memory. We'll be accessing the memory from the NSDF itself. Additionally, there is additional hardware for configuration and initialization, in particular for migrating the live values from the architecture registers on the host core and translating those into Dataflow locations in the NSDF processor, and then back again when the region completes. So that's what the architecture looks like. And now I want to take you through end-to-end with a simple example code, show you how it will get compiled down to the architecture, and then show an example of it running on the architecture, and then why a general-purpose processor wouldn't be able to do as good on this particular workload. So what I'm showing here is a linked list traversal. It's a simple linked list traversal that has a check and computation and store each node. And I'm showing the control flow graph on the right here. I just think that's a little bit easier to look at. So ultimately, what I want to show is the NSDF, this assembly level equivalent of what will be executing on the NSDF architecture. And so this is a little complicated, so I'll build it up step by step. So the first part is to extract out the computation and control instructions. I'm showing those as circles and diamonds here. And next, we are going to add in the explicit forwarding nodes to implement the control flow. And this is a classic Dataflow technique. So what this diamond does basically is take in a control input. If the input is true, we'll send a value along the true forwarding path. And this particular node implements the decision of whether or not to execute the body of this loop. We can use the same concept to implement the control flow at the bottom of this loop. And to start the next iteration, we can have a back edge, which forwards the current linked list pointer. And to start the computation, we just send in the initial value of the linked list pointer. The last step of the compilation is to map these down onto the compound functional units. So let's say I had these two compound functional units. And the technology that I use to do this mapping is the mathematical formulation that I mentioned at the beginning of the talk. But this is pretty simple. We can just do it by hand. So these sets of instructions will map down onto the first compound function unit because they have a add, load, and control. And these two will map down onto the second function unit because they have an ALU and then a store. So that's the entire NSDF representation. And I can show you how this works briefly on a simplified NSDF architecture. So I've labeled these compound instructions CI1 to CI4, and I've mapped CI1 and 2 to the first unit, CI3 and 4 to the second unit. For each of the compound instructions, we have per iteration operand storage. That's where all the live values will reside in. And to start the computation, we send in the initial value of the pointer from the host. So this will get sent into the first compound, the storage for the first compound instruction. These can get issued to the first compound functional unit. And when it's complete, we'll produce values for both the second iteration of the loop and the first iteration of the loop. So we have multiple loop iterations going in parallel. These will be transmitted over the network, and now we can actually pipeline these through the first compound functional unit. And finally, we reach the end of the first iteration, and now we can have we can activate both functional units in parallel. So we're getting parallelism across loop iterations and parallelism across the hardware execution units. So if we compare this to what a general-purpose processor needs to do to get parallelism from the code, it will need to perform speculation of each of these branch decisions. Now, the first branch is very predictable, but the second branch here is actually very unpredictable. And what that means is that either the general-purpose processor would have to serialize on this control instruction, or it will have to suffer misspeculation and recovery overhead. So that's why, actually, for this code, we'd rather use this Dataflow processor. So for some of you who are familiar with the Dataflow research, you might be wondering why I invented some new Dataflow architecture. Why didn't I use some existing Dataflow machine? So I'll break this down into 3 categories. First are classic Dataflow machines. And these are mostly designed for functional languages, which means that they have more exotic memory structures. And they also tend to have very expensive tag matching structures. So that's too much overhead. There are also a number of big spatial Dataflow architectures, one of which is Wavescaler, developed here. And these are designed for massive instruction-level parallelism. And so they tend to be very large. Some of these are actually, I would consider, true feature-rich. They actually try to support general-purpose code in the Dataflow architecture, so they end up needing to support speculation. So overall, these are just high area and power solutions if we want to embed them next to a general-purpose processor. The other class are streaming coprocessors, which have some elements of data flow execution. The existing ones tend to be very good at data parallel code and not so much for other types of code. So these don't work mostly for generality reasons. So finally, I want to talk about some results. And so the way that I study this architecture is by developing a novel cycle level modeling tool, which I'll be happy to talk to you guys about after the talk. And the workloads that we chose were irregular workloads from MediaBench and SpecIt that we chose that are because they're actually very challenging to improve. And I'm going to explore adding the Dataflow architecture to a variety of different general purpose cores, including a small in-order core, all the way up to a much larger out-of-order core. So on this slide, I'm going to show the overall results, geometric mean across the workloads. And on the x-axis here is the relative performance. On the y-axis is the relative energy. These are all normalized to the small in-order core. And this gray line just represents the general purpose core alone. When we add in the Dataflow processor, we get 1.3x speed up and 1.7x energy efficiency over a small out-of-order core. I'm sorry, for the dual issue out-of-order core. We get a little bit less speed up for the large core and a little bit more speed up for the in-order core. But overall, so we're getting some significant benefits transparently, but that's actually not the most interesting result here. What I actually want to explain is why Dataflow makes the most sense inside of a behavior specialization context. So to do that, I've analyzed many different nested loop regions, and I'm going to condense down that analysis on the next few slides. So what I'm showing here are 4 representative workloads from the workload set that we had, and each of these gray bars represents the execution of one nested loop region, and the y-axis is the NSDF speedup over the big general purpose core. Now, the first thing that you'll notice here is that there's a huge range of slowdowns and speedups, and I'll try to break down the reasons for that as follows. So the first reason that we might have slowdown is that we actually might just be vectorizable on the general purpose core. We're going to use the short vector SIMB instructions on the general purpose core, and since we didn't design our Dataflow architecture to be very good at data parallel codes, we get a significant amount of slowdown there. The other class of regions, which are very important, are when the control is on the critical path. So this is the anti-behavior of what we're trying to target. And for these workloads, we really need the control speculation capabilities of the out-of-order core. And finally, there's a few short regions where we can't amortize the overhead of serializing the out-of-order core pipeline and transferring live state and configuring. But this actually isn't very common in very important regions. There are a number of regions that have very similar performance characteristics, and here the control really isn't critical, but there are some other minor microarchitectural differences between the two substrates. But here, we'd still probably want to run these on the Dataflow processor because we get more energy-efficient execution. Finally, there are a number of very high speed-up regions, and we can actually get about up to 2x improvement if we can get if there's enough instruction-level parallelism in the workload. In a few cases, we get very high speed-ups because we can actually exploit more memory-level parallelism, and that's because we can have effectively a larger instruction window than what we could support in a power-efficient way on a general-purpose processor. So overall, the vast differences between the high slowdowns and the high speedups are why Dataflow really makes the most sense in a behavior specialization context when we can choose when we want to apply it. So to summarize, this is an advancement in Dataflow research, which is a very well-established field. And I've shown how we can improve general-purpose processing transparently. And really what I've done here is I've concretized the vision of behavior specialization with one behavior and one accelerator. Now, this might lead us to the question of, well, could we build a system that tries to exploit many different kinds of program behaviors, each with a different kind of an accelerator? And that's what I'll explore quickly in this part of my talk. So the first main question here is, well, how do we figure out what behaviors that we should exploit? And I'll try to do this in an intuitive way by describing one example program classification. And I'll start from the bottom up by explaining what we already know about the accelerator that we already have. So we already know that our non-speculative Dataflow processor is good when the control is non-critical. More generally, we know it's good when there's a high amount of instruction-level parallelism. Even more generally, we know it's good when there's not data parallelism. And now that I've described this hierarchically, we can see that there might be different decisions that we could make and different types of programs that we could explore. For instance, if we have a high amount of IOP, maybe we could exploit very repetitive control flow or very predictable non-repetitive control flow. Or we could exploit non-data parallel codes that have low instruction level parallelism. We could explore data parallel codes that have differing amounts of control flow, because that's often what makes a difference there. And if we have control flow, we might be able to find other types of characteristics, like whether or not there are large data paths that we can exploit. So in this part of the talk, my main contribution here is to show that by specializing for these 4 behaviors, we can actually increase the generality of architecture specialization and get more benefits. And I'll explain just briefly what are the highlights of the accelerator designs that I'll be using. So for data parallel code with low amounts of control, I'm just going to reuse existing SIMD processors that are already very good at doing this. When we have some control flow, we need to find something else. So what we can look at is if we have a very large data path that we can, that's actually separable from the memory instructions in the program region. Now, if we have that, we can offload this data path onto a coarse-grained reconfigurable architecture that can get much more power-efficient execution. If we have a high amount of instruction-level parallelism, but we have very repetitive control, then we can use concepts from trace processors to do coarse-grained speculation and cross-control region execution. So these are the 4 designs that I'll be integrating. And the way that they integrate with the general-purpose core is that the 2 data parallel processors will have a vector interface with the general-purpose core. So the general-purpose core will fetch memory for them. And the 2 more irregular code accelerators will directly access the memory interface. And then, of course, the compiler is now responsible for deciding which of the accelerators that we'll use for any given program region. And this is a very high-level sketch, but there's more details in the papers. So yes, please.
You said earlier that compiler does some heuristics. Does it need any input data like sample data do profiling or anything?
Yes, so I'm assuming that we have basic block profiling in this work. I imagine that this type of approach would be very applicable in like a virtual machine setting where we could dynamically do this profiling at the runtime. The experimental setup here will be, I'll use a similar workloads as what I did before, but I'll be adding in some database workloads and also some scientific computing workloads, just to show the generality of the technique. And then I'll also use an even larger core to show you that actually this can still work. So here's the overall results. Similar graphs as before, performance on the x-axis, energy on the y-axis. And this is just the general-purpose core with no accelerators in it that I'm just showing for reference. And a more standard design would be like a core plus a SIMD accelerator. So that by itself gets you a long way. But when you add in the other 3 behavior-specialized accelerators, we can get significant performance and energy efficiency gains across all of the different general-purpose cores that we integrate with. And interestingly, if we take a relatively simple dual-issue out-of-order core, what we find is that we're covering 80% of the program execution time inside one of these specialized accelerators. It gets more performance than a 6-byte out-of-order core with SIMD, which would be a fairly standard desktop design, with more than 2x energy benefit. So really what this is a processor that has mobile class power and energy efficiency with desktop class performance. So to summarize here, this is just a different way to build a general-purpose core design out of a simple core and out of simple accelerators. And what I'm showing here are transparent integer factor improvements for general-purpose workloads. Now, you may be wondering, well, people have proposed specialized hardware circuits that get 10x, 100x, or 1,000x benefits. How do we get those degree of benefits with behavior specialization? And the secret here is actually that the workloads are different. Yes?
I'm trying to puzzle through how this would interact with simultaneous multi-threading. And it seems like the ones that access the cache probably not so well, but the other ones may be okay. Is that?
Yeah, so simultaneous multi-threading introduces the issue of cache contention and how do you deal with that. So you're right. There's a straightforward way to deal with that when you have the vector interface. It's more of a research question for when you have accelerators that interface over the memory interface. You may want to actually add an additional level of caching between those accelerators and the memory system. Okay, so I just wanted to set up this question of, well, how do we get even more benefits for certain kinds of workloads? So that's what I'll talk about in the last part of my talk, where I'll discuss what I'm calling structured workloads and how we can apply behavior specialization to greatly improve these workloads. So I want to start off with a definition, and I'll give you a rigorous definition. These are just workloads that you would want or need to build custom hardware for. Okay, maybe not a rigorous definition, but it gives you an intuitive sense. So what I'm talking about are workloads like pedestrian detection in a driverless car, where you have vision processing and you need it to respond within 0.1 seconds. And this is just not going to work very well on a general purpose processor. And my claim in this part of the talk is actually that a programmable behavior specialized piece of hardware can give you, for some certain program behaviors, can give you nearly match the benefits of domain-specific hardware. So I want to begin with discussing what are these domains that I'm talking about that we can do well on. So I've chosen the 4 domains that I've taught, and I brought these up at the beginning of the talk: neural network computing, image filtering, database querying, and machine learning. And I've chosen these because they have prominent accelerator publications from the last 4 years. And so what I'm showing here is the microarchitectures of each of these designs. Now, if we just look at these at a high level, I'd argue that they actually look very different. They're very specialized to the particular domain that they're trying to do well on. And that's how they appear to be getting all of their performance and energy benefits. What I've actually done is gone back and looked at what's going on inside these workloads. And in my view, they actually have very striking similarities in terms of what kinds of program behaviors are present there. And I'm claiming that there are 4 main program behaviors across these workloads. And I think these actually define what structured workloads are. So the first main behavior is that they have highly regular parallelism, and a lot of it. And if they didn't, we probably wouldn't be able to get any benefit really out of hardware implementation. We'd rather just run on the general purpose processor. They also tend to have very well-behaved data reuse patterns. We know what data we're going to use ahead of time, and this can typically be thought of in coarse-grained fashion. We have a potential for immediate use of data and consumption of data as opposed to storage and retrieval through a general purpose register file or memory. This is like another way of saying they have a very high computation to memory ratio. And they also have very repetitive and simple algorithms that are typically exploited by very simple hardware implementations. So if this is true, let's go look back at these hardware designs again, but now putting on our behavior specialization goggles. What I argue that we find is that actually they are all specializing for these same 4 program behaviors, just in a domain-specific way. So they're all specializing for regular parallelism by using independent processing elements. They're all specializing for data reuse by using custom streaming scratchpads. They're all specializing for the immediate use of data by using explicit operand networks, and for algorithmic simplicity by using either statically scheduled or coarse-grained controllers for the rest of the hardware. This is actually a good thing because the fact that they're all exploiting these program behaviors can give us the confidence that we can actually build a programmable piece of hardware that specializes for these same behaviors, but in a programmable and flexible way. So that's what I'll try to do on this slide, where I'll describe the Structure Specialization Fabric, or SSF, which is a behavior specialized accelerator for the behaviors that I mentioned. And I'll explain this design from the bottom up at a relatively high level. So to specialize for regular parallelism, we're going to use an array of independent processing elements. I'll integrate these inside of a spatial fabric to specialize for the immediate use of values between the pieces of hardware. And I'll also use a DMA engine to specialize for the immediate use of values from memory. We can add a programmable scratchpad to specialize for the data reuse inside of these algorithms. And to specialize for algorithmic simplicity, we can add a tiny microcontroller that simply coordinates and controls the rest of the hardware at a coarse granularity. And then if we need more parallelism, we can simply tile this design in a standard way. So, okay, doing this, of course, will add power and area overhead because we've added in a programmable network and a programmable core. And the real question is, well, how much overhead is this? So that's what I'll try to answer in the last part of my talk. And I'm going to compare SSF against the 4 domain-specific accelerators that I mentioned. And we validated our modeling approach against data that each of the authors of these papers has generously provided us. And I'll make this comparison in 2 ways. First, I'll do something called domain provisioning, where I configure some of the aspects of the tile, like the number of tiles and what functional units are inside the tile, to meet the performance requirements of a particular domain. And then I'll also show a balanced design that can meet the performance requirements of any of the 4 domains, so that basically we can replace having all 4 domain-specific accelerators. First, in terms of performance, the domain-specific accelerators across these different applications get speedups over a general-purpose processor in the range of 10 to 100x. And the structured specialization fabric gets around the same performance level, and that's because we provisioned them to have enough resources to match the performance. And again, the real question is how much power and area overhead is there? So that's what I'll show here. So across the 4 domain provision designs, the area and power, the area overhead is on the order of, if we ignore the database accelerator for now, is on the order of 25% to 4x, depending on the workload. And the power overhead is in the range of 2 to 4x. Okay, so that is something. If we look at the balanced design versus having all 4 domain-specific accelerators, we can actually save an area because we don't have to have all 4. But of course, we still have that power overhead. So the main disadvantage of having something like a structured specialization fabric appears to be the power overhead. And interestingly, this power is on average only in the range of hundreds of milliwatts. So in many systems, 100 milliwatt power is actually going to be noise in comparison to the many watts of, if you include memory power or cache power or other elements of the architecture. So this power overhead might actually, depending on the situation, might not affect the energy efficiency very much at all. So to summarize here, the structured specialization fabric can match to the performance of a domain-specialized architecture given the program behaviors that I talked about, with nearly identical energy efficiency. It's programmable, and it's tunable to different kinds of domains. So to conclude the talk, what I've talked about here is how to apply behavior specialization, both for transparently improving general-purpose processors, and also for creating specialization fabrics that are very good at certain kinds of workloads. And really, the implications of this, I think, can be stated as follows. General-purpose improvements are not over. There's still a long way that we can go to take architecture without even relying on technology scaling. And so what this means is that it's an exciting time to be a computer architect. There's a lot we can do. But also, it's sort of ironic because the reason that we have all these potential benefits from specialization in general-purpose processors is that we have architecture specialization of a limited form. So that said, I want to wrap up my talk by discussing what I think some of the critical challenges in computer architecture are going to be moving forward and how that relates to what I want to look at next. So I'll just summarize this in one word as cost. So why do I think cost is a big deal? Well, according to ARM last year, as estimates made last year, the cost of doing a mobile SoC design, system-on-chip design, is going to be in excess of $250 million by 2018. And this doesn't include manufacturing, which is actually much less. And this cost is because these systems are getting so complex. And what I'm arguing is actually we need to find a way to tame this complexity to create lower cost designs. And if we can create lower cost designs, then I think that we can provide more value both to applications and to users. And I think this can manifest itself in a number of different ways. For instance, this might manifest itself as heterogeneous multi-cores where we can specialize across the cores, across caches, and across the memory system, and actually optimize across all these different dimensions. But we can also apply this to very different domains. Like we might have IoT networks or sensor networks where we want to have specialized hardware for performing specific computations, but we still want to be able to reprogram these in the field. We We can also apply this to the very hot topic right now of near memory computing or near disk computing, where we want to have radically different architectures to meet the performance requirements of these different data systems. And then finally, we might have limited heterogeneity in our data centers and transparently improve the very diverse kinds of workloads that we'd have in these settings. So overall, there's a lot of opportunities, but the problem is with our current style of design. So I explain the way that we're currently doing design like this. Basically, anytime we want to build a specialized architecture, an architect is going to look at the programs that are very important, do analysis, exploration, perform design, build the ISA, implement, and finally we'll come up with some specialized architecture. But we're not even done yet, because these specialized architectures get performance by just getting rid of existing ISAs and exposing their own internal resources. So what that means is that we'll need compiler writers to do program analysis, optimization, scheduling, code generation, and then finally we'll have a compiler that can match any of the specialized architectures. This is a process I've been through in my own graduate career. It takes a long time, even to do a good job on one accelerator, into months or years range. So what I want to do is rethink how we do architecture design and think if we can come up with higher level ways to do architecture design. And what I'm imagining is that we can encode all the knowledge that we have about specialized architectures into a more abstract architecture specification language. And if this language is rich enough and expressive enough, then we can use it to generate not only the architecture that we care about, but also to generate a compiler that can target that architecture. And now, if this is successful, we can actually do design space exploration across a much wider variety of designs and potentially even create much more heterogeneous systems in the future. But there's no reason to actually stop here. The architects still have some work to do here, and we don't like that. So there's no reason that once we figure out what these high-level knobs are inside the architecture specification language, we can actually embed these as decisions inside of some optimization framework. And now, instead of the architects guiding the design, we can do program-driven design. And the way this would work is that we do characterization of the programs, maybe use different kinds of program clustering algorithms, and use that as inputs into the optimization framework, along with design-level constraints like power or area or throughput, and then use those constraints to develop architectures that perhaps we've never thought of before, and also the compilers that can support them. And if this is successful, in some ways, this is the holy grail of computer architecture, with the unfortunate side effect of perhaps putting some architects out of a job. So with that, I'll just thank you for your time and attention, and I'll be happy to answer any questions.
We have time for a few questions.
Yes, please.
I'm just curious, your CGRA, which you didn't show the architecture for, but how different is it from your SSF, I think? Because it seems like that's something that could vaguely fall under some definition of a CGRA.
Okay, so your question is, how different is the CGRA design and the behavior specialization and the transparent specialization versus the structure specialization fabric? Okay, the designs are similar in their topology. They're both coarse-grained reconfigurable architectures. The CGRA that's in the transparent specialization work needs to be more general, and so it actually has flow control, so it can tolerate arbitrary memory latencies. The CGRA in the structure specialization fabric is completely circuit switched with no flow control. All the timing has to be enforced at the boundaries, and we're doing that to get much lower area on that design, because we want to be competitive with domain-specific hardware. Yes?
So the behavior specialization, you identified as this point of specialization between domain and general purpose, right?
Sure.
Is there another bisection point where there's between behavioral and domain-specific, where we might have more specific behaviors that still cover wide-ranging programs?
Yeah, I absolutely think there is actually a wide range of specialization techniques, all the way from general purpose processors to what I'm doing, behavior specialization. I'd put GPUs in the middle somewhere. I'm after that is something like the structured specialization fabric that I talked about, and then on the far end is more application-specific hardware. I think you can get, if you want to take the behavior specialization and make it more specialized, there's certainly lots of things that you could specialize for. More specific computational structures. You could specialize for different kinds of data types and modify the data width of the architecture. And there's all sorts of different kinds of program behaviors that we can split this into. I think this is just the beginning of the research in that area. Louis?
Yeah, so do you have a sense of what is the difference in potential between SSF and a full-blown ASIC? How much more room do you?
So the question is, how much room is there between SSF and an ASIC? So the way that I look at this is that we can, for the types of programs that I've talked about where we have these certain properties, we can basically just keep growing the architecture to meet the performance requirement, and it's really just how much power and area overhead is. So far I've only compared against these domain-specific accelerators, which are arguably semi-programmable, and so there's another level of improvement. I think it's in the range of 1 order of magnitude to give you some answer on how much area power or area overhead, but it would depend on the domain, of course.
So, am I right to think that most of the benefit of SSF comes from effectively reducing the dynamic overhead of control structures? Or is it from aggregation of operand? Where's the performance
coming from? The performance is coming from the fact that you can you have very regular memory access patterns that you can access in a streaming way, and you can basically get each of the functional units in the CG array active on every cycle. And so it's just a matter of exploiting memory regularity, I would say.
So your work is very processor focused, and do you have thought at all about specialization in the memory system or elsewhere in like the whole system collectively, or?
So your question is, have I thought about the ways we can specialize other parts of the system, including like the cache hierarchy, or doing specialization across inside of the memory system? I think that's important. We'll actually need to do that. One of the things that you could do is, for any given accelerator, you could figure out, well, what exact cache interface would I like for given these certain kinds of programs that I have. Right now, all of these accelerators are sharing the same cache interface. So you could definitely co-optimize the caches and the accelerators together. I think that's what we'll need to do. You could consider adding different kinds of programmable memory structures into the core. That's also a possibility. Maybe add support into programming languages. And I think a lot of the interesting architecture work is going to be in near data processing and in memory computing, where we can actually greatly change the underlying architecture. And people are willing to look at these very different architectures. And there's a big question of what should we put near memory. So I think there's a lot of opportunities there.
All right, thanks, Tony.